Okay. Okay, you have also some data and images in in a folder that is named example data. Do you have it? Okay, you can go to the shapes, diamictite, tracing, or diamictite JPEG. This is just the picture of the form of the diamictite. Ah, okay. Okay. And if you would like to digitize the shape to gain the information, oh, this is very small. You can use maybe this one. Okay, you click on this symbol, and you have a choice of a center point, ellipse axis, 5-point ellipse, quadrilateral shape, filled shape, line pair. Okay, we can try with filled shape that just you put the mouse on the object, you click, and nothing happens. Ah, okay. In this way, we found a good boundary with the object and depicted the strand ellipse with the long axis, short axis, and centroid. At the same time, is recording the data in a file like this. Maybe oh, there are other objects in this way, in this form. Identification of the object, 1, 2, 3, 4, long axis, minor axis, the area, axial ratio, orientation, and so on. So you have all the data that you need to calculate strain. And you can go ahead. Yeah. Sorry? Ah. Yes, yes. Also, yeah, you can use 5-point or center point, for example. Just you put here. Okay, there is also some this, but the best one, I think, is to use a fine point ellipse. So you can choose your object like this, 1 point here, 1 point here. You can see the yellow dot, 3, 4, and 5. Okay. In this case, there is not a good approximation of the ellipse, so I try to do another time. So we can try with this one. 1, 2, 3, 4, 5. Here is a little bit better, but a little bit longer. Okay. In this case, the 5 point were put in a better way, because if you put, for example, the point very close, nothing happened. Nothing. Okay. Nothing. Okay. The Stan ellipse is very strange. So try to be accurate in this kind of feature. Another possibility is open image. Okay, you can use the trace. So in this way, maybe it is more easy. This is the noise of the program. When there is an error, oh, In this way, it is very quick formation. Yeah. Yes. Yes. Yeah. Maybe. But if you are okay. Mhm. Okay. Anyway, if you have a good picture, it is not so long to find the 5 points along the perimeter. So I suggest to use a picture just to be more quick. But up to you. It's not a problem. Okay. Okay. After that, when we have made a lot of these kind of measurement, maybe 40, 50 objects, you can try to plot, maybe free plot. Okay. Oh, this is from another picture. Oh, because I uploaded before uh, another picture, but he plot all the centroid data, the position, and they made automatically the free plot to calculate the finite strain. And the finite strain, okay, if you put the mouse on the free plot, on the RFI plot, he created this kind of plot with RFI method, or maybe the clues plot. The clues plot is just a plot used at the beginning in the 40s, in the 50s by an American geologist working with deformed holites, and they put just on the horizontal axis the minimal, the short axis of the object, and here the long axis. And they usually, if there are no big problem of deformation, the object are nearly spherical, all the data should be aligned along this line. And in this way, you can calculate the strain. Obviously, different angle of the line indicate different strain. R equal to 1, R equal to 10. So, but in this case, you can see that the objects are very far from one line. So this means that they are not perfectly spherical, but different elliptical shape. So it is not good. It is not good to use this kind of a graph here. Maybe the RF graph is better. This kind of line, this R, axial ratio, the phi orientation, this kind of line are line of initial axial ratio of the object. So if you have point that fit several lines, you mean that in this case, you mean that you have different initial axial ratio of the ellipsoidal object in the deformed rock. But it is not a problem for this. I do not. Good. Nice. This one do. It's strange. Mhm. in paper with black and white borders, and just to use the fill option. Just you click in this position and they calculate the area, the perimeter, the long axis, short axis, orientation, the centroid position, and the data are put in a file like this that you can, well, much data, that you can save somewhere, save as in some place, okay? And before saving or after saving the data, you can plot. You can use the fly plot, not so good in this in this file, or the earthy plot that is quite nice to. You have several point plotted, the line of initial axial ratio, and the red dot is just the position of the axial ratio of the strain ellipse and the orientation. Usually when I click here, appear the axial ratio below, but now not now, but just we checked. Sometimes the program has some problem in adapting to several objects. Anyway, if it is 1, 2, 3, 4, this close to, I don't know, for this 1, 2, maybe 1.7, and the orientation is maybe 28, 30 degrees, 29, 30, okay. Yeah. But usually when you click here, you have just below the position in the graph, so the axial ratio. I don't know why it doesn't work. Okay, we can close this plot. Another way is to calculate ellipse, to select some mean radial length angle vector. This is made by calculation of 2D tensor, and the centroid. If you click OK in this page, oh, they give the result of the close plot. The close plot is where is close plot? Close plot is this one. It is not a so good graph because you have a lot of data here along this red line, but some data are along different lines. This means that the objects are not spherical, but with different ellipticity. So the data is not so good. But anyway, just a tentative. But in this file, oh, you have close plot results. You have the axial ratio is 1.4, because very different to 1.9 or 2 because of the confusion between elliptical object. In the other part of the file, you have mean ellipse calculation by maybe different kind of mean, arithmetic mean, or standard mean, or another different kind of mean. So you can read here the R is the axial ratio is 2.1.02, and C is orientation of the long axis. 22, here 2 and 22, so more or less are the same value. This software gave a lot of statistic, but more or less with natural data, there's no big difference in between different methods. Okay, the harmonic mean, arithmetic mean, the harmonic mean, and the circular mean, a different kind of calculation with small differences. The arithmetic mean give a little bit higher value, 2.4. The harmonic mean is very good, 2.1. The harmonic mean is just dividing the number of objects, dividing the axial ratio elevated -1 plus axial ratio elevated to -2. So a little bit different calculation that usually people found that is very close to the real strain of the object. So harmonic mean is a good approximation. And when, okay, so you can use for strain in just this simple way. The best use is for the fry graph. Of course, I have no good large number of objects in my picture because I open again the image. Okay. But there is a reason why the fry plot is not so good, because the fry plot is better used if the objects are of the same size. So this is a limitation, but you can check using this kind of plot. Because if you use the same object with the same size, when you plot, you put here the center, you define the other point around. So the high strain area with a lot of points is just is a good elliptical shape. But if you have a small object or bigger one, the small object, when you point your center here, go inside the void area. If you have a lot of these small objects, you have a confusion. This larger one has a distance very big, so from here, and when you have different sizes, you have confused strain ellipses, or in this case, not enough point, but there are too much different degree size and not good approximation of the strain ellipse. So it is important because can check the graph, the plot, so directly, because you made the calculation, you plot, you say, okay, oh, in this case it is a bit better because I put away some graph, but anyway, you can see the general shape could be this one, but there are several points inside because of the smaller object present here. So anyway, you can use the RF graph. You can gain the information about acceleration and orientation. Also on the fly graph, you can use. Okay, the centroids are here. Okay. Okay, these are information. Anyway, you can calculate the strain ellipse by digitizing 5 point here and then calculate the strain of this picture. And you can compare the result from this strain and the strain obtained by the LFIB. If the results are similar or with small difference, it's okay. If the results are strongly different, means that there is a competence contrast in between the cluster and the matrix. And so you have maybe to avoid the RF calculation and use the fry graph calculation. And this is just the first step because you have this graph. This is just a surface. So remember that you must use one principal plane, maybe Z or XZ. You are using this one. You need to use another one. So with two principal planes, you are able to plot your sample in a clear graph. Maybe your sample for here, the flattening field. We can also calculate the distance from the origin of this point. So much more strain. Put the point far away from the origin, just 1.1. So you can make some estimation of the formation different way. But you need at least two surfaces to have a 3D deformation and to correctly plot in the free graph. And if you are stuck the main center thrust, that the main center thrust here. Okay. You can collect sample from here. You calculate two section here, two section here, and then the 3D. In this program, you can gain the information about several things, but at the end you have R here, acceleration and orientation. And you can use also this data to plot, to calculate vorticity. Of course, in not the same rocks, because when you use rocks for strain analysis, you have an object, an initial object that has been deformed and became elongated and underwent also some rotation. But the deformation and the rotation. For vorticity, you need to have strain. For vorticity, you need to have a rigid object that rotate during deformation, during single shear or blue shear, but without internal deformation. They are strongly rigid and rotate continuously or not continuously, but the input data, you can get the input data also by this program. We can use the 5-point perimeter and we calculate the long axis, short axis, centroid, orientation, and the acceleration and the orientation are such that are data that we can use for vorticity. You remember the graph because for vorticity analysis using Porphyroclast, we use the orientation alpha, the acceleration here, 90 minus 90. Here, 1, 2, 3, 4, 5. Acceleration may be 1 and orientation 20, the point is 0, 2 and orientation 20, the point is 0, 2 and orientation maybe 45, the point is 0. So you have this kind of distribution, you detect the LC value, and you calculate the vorticity. But instead of gain manually the data, you can take a picture and upload with solve fit, ellipse fit, and digitize the boundary with 5 points. And so in the file you have acceleration and the orientation. You can select this column and try to put in Excel to put the value to calculate this graph. But I know it's just this. There will be time, but for this, okay, there is a graph. Okay, there is an Excel file. Okay. Excel is opening. Made by Xipolias or Fossen, where you can put your data. So this is the graph for vorticity. Is the shape factor, B or the acceleration, not so much difference. And the angle between the long axis and the macroscopic foliation. And here you can put the short axis, long axis, ratio, or angle. Now there is no value. Don't know why. Okay. But anyway, in this column you can put your data, and automatically they are plotted on the graph. So just you collect the data from an sheet, put here. I don't remember if this column is set in the same way. Anyway, you put acceleration and angle, and you have the point here. So you can calculate also vorticity with the same data. But remember that for strain, the cluster should be deformed, so they rotate due to deformation. In vorticity, they should be rigid like this, so they rotate but not deform for vorticity. For strain, you have to deform the object. So different bases. You use the same acceleration orientation, but the basis is completely different. So you cannot apply vorticity and strain on the same object. Sometimes people do this, but it is not correct. Okay. Okay. So there is some question. Let's try to understand why this not work. It's almost clear. So just so how to start to work with this software LipsFit. If you need, you can continue, and you can download also the manual of the program. It's very big, not easy, because there is a lot of statistics with respect to the initial version 1.1, 2.0, big statistic inside, but you can avoid most of the statistic if you use for fine strain. There is also a possibility to use displacement and kinematic calculation for GPS data, velocity data. So if you in the future will face this problem, you can use this fit. You can read the manual to understand how to manage this data, this kind of data. Okay. Some questions? Okay. Okay, thank you for your attention. Tomorrow, Mahesh Nakur will tell you some about landslide and so on, and we will see you the day after tomorrow for the last day. We will speak about a lot about Himalayas, okay. Information models, information trust, high fellowship zone, such more interesting things. Okay, thank you very much. Yep.